What does this video of Vladimir Putin?
America. You blame me for interfering with your democracy, but I don't have to.
These models and Joe Rogan have in common?
Also, since my brain is connected to the internet, I've become a medical expert. Did you know that bacillar membrane and otolaryngology are not autocorrelation?
None of these three videos exist. They were all created artificially by a deep learning architecture called GANs. GAN stands for Generative Adversarial Networks, and they've had a huge impact in the deep learning industry for the last couple years. Today I'll be showing you exactly what a GAN is and giving you 3 core examples. This video is not meant to be an introduction to deep learning, so I do expect some prior knowledge in neural networks and especially in convolutional neural networks. I recommend these 2 videos on these topics, and I will provide some links in the description. A GAN consists of 2 neural networks, a generator and a discriminator. The generator takes some random input and creates an output. The output could be an image or a sound depending on what type of data you're processing. The discriminator classifies examples as real or fake. So given a real example, it should output a number close to 1, but given a fake example, it should output a number close to 0. The authentic examples come from the training data set. The generated examples come from the generator when it's given some random input. The Minimax Loss is a very common loss function for GANs. Let's break this down. G of Z is the generator's output given some noise Z. D of X is the discriminator's decision on real data, so optimally it should output a number close to 1. E sub X is the expected value over all the training data. D of G of Z is the discriminator's decision on fake data, which was created by the generator. E sub Z is the expected value over all random inputs, which are used for the generator. The discriminator's motivation is to maximize this function. It can do that by classifying the real examples as real and the fake examples as fake. The generator, however, tries to minimize this function, and it can do that by tricking the discriminator. The Minimax Loss isn't the only loss function for GANs. Here are 2 other common ones: the modified Minimax Loss and the Wasserstein Loss. We'll be going over 3 main examples for GANs today. We'll be going over the StyleGAN for image generation, the CycleGAN for image-to-image translation, and the StackGAN for text-to-image generation. The StyleGAN was first introduced by the NVIDIA research team in a paper titled A Style-Based Generator Architecture for Generative Adversarial Networks. Many of the early GAN papers focus on the discriminator and ignore the generator. However, the team at NVIDIA did the opposite. They focused solely on the generator and kept the discriminator and the loss function mostly the same. They made 5 major changes to the generator. We'll be breaking down these 5 changes in detail. Their baseline architecture was taken from another NVIDIA research paper titled Progressive Growing of GANs for Improved Quality, Stability, and Variation. A progressive GAN starts with a very basic model for the generator and discriminator. These models get trained, and then more layers are added as training progresses. This repeats until we've finished with the final architecture for both the generator and the discriminator. The next major change they did was replacing the nearest neighbors method for upscaling with the bilinear method. With the nearest neighbors method, the small matrix is projected on the bigger one by just copying the values in the initial matrix. So here you can see 10 is copied 4 times in the second matrix. However, with bilinear upscaling, we use a distance-weighted average of the initial matrix to get the larger one. So the values in the second matrix are a combination of the initial one, based on their distance. With the regular generators, the random input is only taken at the first layer. But with StyleGAN, this input first gets mapped with a mapping network, F, into an intermediate latent space. And then this latent space is fed into the synthesis network. It is fed into the synthesis network with these ADA-in calculations. ADA-in stands for Adaptive Instance Normalization. where you take a W, which is from the intermediate latent space, and map it to style vectors, y sub s and y sub b. Y sub s is the scaling vector for styles, and y sub b is the bias vector for the styles. These two can be created with fully connected layers. After you normalize the data based on the instances, you multiply it by y sub s and add y sub b. These added-in layers happen after every single convolution. Random noise is also added into the network. This random noise corresponds with small details in the final product, like strains of hair and freckle patterns. The last major change they did is mixing localization, where they use two latent vectors on some of the training sets. One of the latent vectors is used for some of the added-in layers, and the other is used for the rest of the added-in layers. Here is a good example of mixing localization. All the images in the top row and the left column were created using one latent vector. All the images in the center are created with a combination of the latent vector from B and the latent vector from A. Let's look at this specific example. This image used its coarse styles from B and the finer styles from A. As you can see, it's very similar to B, with finer details taken from A, like the skin color and the hair color. This image takes its middle styles from B, and because of that, it looks like a good combination of both. It doesn't look like either A or B in particular, it looks like a merger of those two. This image takes the coarse styles from A and the finer details from B. As you can see, this image mostly looks like the A example with finer details from the B image. If you want to learn more about the StyleGAN, I recommend this follow-up paper by the NVIDIA team, analyzing and improving the image quality of StyleGAN. In this paper, they made several modifications to the original StyleGAN to get better results. Next, we'll be moving on to CycleGANs. CycleGANs originated in this paper by Berkeley AI Research, unpaired image-to-image translation using cycle-consistent adversarial networks. CycleGAN is used for image-to-image translation. As you can see in this example, we take a painting by the artist Monet and turn it into a regular real-life photo. We also do the inverse, take a real-life photo and turn it into a painting by Monet. In the other example, we take pictures of zebras and turn them into horses. And the inverse again, we take pictures of horses and turn them into zebras. Most neural networks required paired examples in the training set. However, for CycleGAN, we don't need paired examples. We need one domain X and a domain Y, and these do not need to have individual connections to each other. In this case, domain X is of real photos, and domain Y is of paintings. In CycleGAN, we have this function G, which turns an image from the X domain into an image from the Y domain. The researchers found that if you only have one function G, we cannot guarantee that the mapping between the image in X and image in Y is meaningful. They could be completely different images, just in separate domains. Also, only having one function G leads to mode collapse, which means that multiple images in X map to the same image in Y. The solution to these two problems is to have a inverse to G, which is F, which takes an image from Y and turns it into X. Both G and F are generators in our architecture. The generators use a encoder-decoder model, where they take the input image from one domain, encode it to a certain layer, and decode it into the other domain. The decoder also has these skip connections. The discriminator is a 70 by 70 patch GAN. What this means is, it goes through the image in 70 by 70 portions and checks if that part is real or fake. The big difference between this and a regular discriminator is that a regular discriminator gives you one output, telling you if the entire image is fake or not, which will be between 0 and 1. But in this case, we'll be having a matrix, and each entry in the matrix tells you if a 70 by 70 portion of that image is real or fake. The loss function for CycleGAN has two components, the adversarial loss and the cycle consistency loss. We'll start with the adversarial loss. Here is the regular Minimax Loss function. All we have to do is make some modifications so it's using the correct data. It's very similar to the regular Minimax function, but now we're taking the real images from the other domain. The loss function for F is very similar to G, but now we just switch the positions of the images. In total, we have 2 generators and 2 discriminators. In training, the researchers found that replacing the negative log likelihood version of the loss functions with a least squares loss provided better results, but both these loss functions have the same objective. The other portion of the loss function is the cycle-consistency loss. Now G and F should be complete inverses of each other, and this makes sure that that exists. We should be able to take an image from the X domain, apply G, and turn it into an image in the Y domain, and then apply F, and turn it back to an image in the X domain. These images in the X domain should both be the same. By taking the difference between the first image in X and the second image in X, we get the cycle consistency loss. The cycle consistency loss is measured in the forward direction and the backward direction, depending on which image we start with. Here is the equation for the cycle consistency loss. The first term measures the forward cycle consistency loss, and the second term measures the backward cycle consistency loss. The total loss function now looks like this. The first 2 terms are the adversarial losses for the 2 different GANs, and the last term is the cycle consistency loss, which measures both the forward and the backward loss. Lambda is a hyperparameter that determines how important the cycle consistency loss is compared to the adversarial losses. This can be changed during training time. This picture illustrates why each component of the loss function is needed. We get the best results when we include the GAN loss and both the forward and backward cycle consistency losses. The final GAN we're going to go over is the StackGAN, which was first introduced in this paper. StackGAN, text-to-photorealistic image synthesis with stacked generative adversarial networks. The StackGAN is used to generate images using a phrase. So in this example, we have the phrase, "This flower is yellow in color with petals that are vertically layered." We have 2 different rows of images corresponding with different stages in the StackGAN. As the name might suggest, StackGAN means that there are multiple GANs in this architecture. So stage 1 represents one GAN, and stage 2 represents a second GAN. This image shows the difference between StackGAN and other models used for text-to-image generation. As you can see, StackGAN is superior to the other models given the same phrase. Before I start breaking down the StackGAN architecture, there are 2 topics that I would like to cover: variational autoencoders and conditional GANs. Learning these 2 topics will make understanding the StackGAN much easier. Regular autoencoders take some image, encode it to some bottleneck layer, and then decode it back to the original image. So the input and output should be the same visually. The bottleneck layer contains all the attributes of the original image, so it can be decoded later on. These attributes are stored as discrete numbers. However, with the variational autoencoder, rather than having a bottleneck layer, we have a mean vector and a standard deviation vector for each of those attributes. So rather than building an encoder which outputs a single value to describe each latent state, we'll formulate our encoder to describe a probability distribution for each latent attribute. This enforces a continuous, smooth latent space representation. Let's look at one attribute in particular: smile. With the regular autoencoder, smile is stored as a discrete value for each image. However, with the variational autoencoder, this data is stored as a probability distribution. So the decoder is given a sample from this data to recreate the image. So now, rather than storing discrete values for each of these attributes, we store a probability distribution for each of them. There is one problem with variational autoencoders that we need to address. You cannot backpropagate through a random node. Therefore, you cannot find the gradients and perform gradient descent. To solve this, we use a reparameterization trick, where we still keep the means and variances, but we introduce a variable epsilon, which is normally distributed with a mean of 0 and a variance of 1. Now, the attribute that we're going to decode is a combination of these 3, but the only part that is random is epsilon, so we can propagate through all the other nodes. This gives us a way to find the partial derivatives of all the other deterministic nodes. aside from epsilon. Then we can perform gradient descent on these nodes. Now we have a model that gives us probability distributions for each of those attributes. We take a sample from this data, feed it to the decoder, and recreate the original image. Now let's move on to conditional GANs. Here is the regular GAN model. Conditional GANs allow us to feed an extra variable to the generator and the discriminator, called the conditioning variable. This conditioning variable will give us extra information on what to judge and what to create. For example, if this GAN was used to create images of dogs, the conditioning variable could be the breed of dogs. So if we gave it a breed of golden retriever, the generator and discriminator have more information to act on. Now that we know about variational autoencoders and conditional GANs, we can look into the full stack model. Don't worry if this looks a little bit confusing at first, we'll break it down into individual parts. First, we take the text description T, which is from the paired training dataset, and put it through an embedding layer. Now the embedding layer could just be a fully connected layer. This embedding is used for both the generators and the discriminators as conditioning variables. Before it gets sent to the generator, it goes to the conditioning augmentation layer, where it's broken down and sampled from a vector of means and a vector of variances, like with variational autoencoders. There's also an epsilon from the reparameterization trick. The conditioning variable C hat is sampled from the distribution in the conditioning augmentation layer and sent to the generator along with some random noise, which is normally distributed with a mean of 0 and a variance of 1. This is upsampled in the generator to create stage 1 images. These are low resolution images of 64 by 64 that have the main components of the image but not the finer details. These are compared with other 64 by 64 real images that are downsampled and sent to the discriminator. The discriminator takes the real images and generated images and classifies them, along with the conditioning variable of the text embedding that we initially got from the first layer. The image created in stage 1 is sent to the second generator, also with the text embedding. The second generator has its own conditioning augmentation layer. The second stage generator uses more of an encoder-decoder process, where it takes the image from stage 1, the text embedding, puts it through its own conditioning augmentation layer, getting C hat, which will now be the conditioning variable, and uses both of them to encode and then decode the final 256 by 256 resolution image. Finally, we have the stage 2 discriminator, which takes the real images and generated images from stage 2, as well as the text embedding, and decides whether the images are real or fake. The loss function for StackGANs really is this Minimax Loss, but with a lot of notation. Let's start by breaking down the stage 1 discriminator loss. The first term here has to do with how well the discriminator can classify real images. Where I sub 0 is the real image, phi sub t is the text embedding, and d sub 0 is the stage 1 discriminator. The second term checks how well the discriminator can classify generated images, where g sub 0 is the stage 1 generator, z is a random noise variable, c hat is the conditioned variable, which is the text embedding after it went into the conditioning augmentation layer. We also use phi sub t as a conditioning variable for the discriminator as well. The discriminator tries to maximize this loss. Now let's move on to the stage 1 generator loss, which looks like this. First term checks how well the generator can trick the discriminator into thinking that its images are real. Now the second term is the callback-Lieber divergence. The callback-Lieber divergence returns the difference between two probability distributions. Having this in the loss function encourages the conditioning augmentation section to produce means near 0 and variances near the output image. Lambda is a hyperparameter which allows us to control how important the callback-Lieber divergence is when training this network. The second stage losses are pretty much the same, but instead of using the low resolution images for the discriminator, we use the full resolution images. And now the generator takes the output of the first stage GAN as its input, rather than the random variables. This applies to the stage 2 generator loss as well. So this completes all of the GANs that we wanted to cover today: the StyleGAN, the CycleGAN, and StackGAN. Generative adversarial networks have been making huge waves in the deep learning space for the last couple of years, and I for one am very excited on the possibilities of applying these to real-life applications. Though we only covered image generation today, I want to emphasize that GANs can really work with any data type. Two separate examples are the audio generation GANs and the text generation GANs. I hope you all enjoyed this video and now have a better understanding of what GANs are and some specific examples of their applications. Thank you for watching.